Good afternoon, everyone, and welcome to session number 2 of day 2 here at ETE 2021. I'm Matt Swartley with Chariot Solutions, and I would like to introduce you to Mandi Wise, who is a solutions architect with Apollo Graph Incorporated and the author of Advanced GraphQL with Apollo and React. Mandi is going to speak with us today about Apollo Federation and how we might move away from a monolithic GraphQL API. So please welcome Mandi Wise.
All right, thanks so much. Good morning, good afternoon, and good evening to everyone. I'd like to begin by thanking you for joining me for this talk today. But before we jump into the content, I'll share just a little bit about my background. Again, my name is Mandi Wise, and I've been doing full stack development with GraphQL for over 4 years now, and I currently work as a solutions architect at Apollo. So that means that I get to work with Apollo's enterprise customers to help them transition to Apollo Federation and expand GraphQL adoption across their companies. And in addition to that, I've also authored and co-authored a couple of books about GraphQL. And today, I'm very excited to talk to you about how you can supercharge your data graph with Apollo Federation. So to begin, we'll first explore the current API landscape. Then we'll see how a common federated data graph can simplify and speed up the work of API contributors and consumers. We'll also take a closer look at how Apollo Federation works and what it takes to migrate to a common data graph from a monolithic GraphQL API. And finally, we'll wrap up by exploring what managed federation is and how it supports the safe, continuous evolution of a GraphQL API. So before we jump into the what, why, and how of federated data graphs, let's begin by talking about some common architectures that developers presently encounter and where APIs fit into that picture. In larger applications today, the backend architectural boundaries are often drawn between logical units of functional isolation. And each of these loosely coupled services is often the responsibility of a single team to manage. And at a high level, something approximating what we see on the screen here is what we imagine when we think of microservices. But this idea may also extend to modular monoliths as well, where each service in the diagram could also represent some clearly defined boundary within a monolithic architecture. So on the surface level, this is great because we can think of each of the services representing various business capabilities. And those capabilities can be bundled into solutions for users that they conveniently access via the client applications that they interact with. And also worth noting is that these solutions may be for both internal and external audiences for a company because we can compose those capabilities together to serve different groups of users and their use cases as needed. In reality, though, the diagram of relationships between services and client applications may be a bit more complex. Without an intermediary in between, you end up with a lot of point-to-point connections between services and client applications. And when any new service or client application is added into the mix, the overhead of adding that new component is multiplicative. And I think it's fair to say that what we have in the middle could hardly be described as solutions, but rather a lot of overlapping network requests where individual clients ultimately become responsible for wrangling the data that they need and from disparate endpoints, and with a lot of juggling of bespoke logic to do this. So what we have here is a recipe for increasing complexity, an architecture that becomes difficult to reason about, and a lot of unnecessary duplications that throttles how fast you can ship and build new features. So to address these challenges, backends for frontfs, or BFFs, have been one recent solution. BFFs are tightly coupled to a particular user experience. And again, on paper, this may sound great, but as time goes on, BFFs are doomed to feature drift and duplication. For example, depending on how strictly BFF usage is enforced, various occasions may arise where a client app piggybacks on another client app's BFF for some reason or another. Or in an alternative scenario, the iOS and Android apps in this diagram may initially share a BFF, either by design, and to generalize its interface enough to serve both mobile client teams. But these teams may eventually find that their needs have diverged just enough that they need to develop more specialized BFFs for each use case, but there will still be significant duplication between them. BFFs can become a bottleneck too when a new service is introduced. Depending on who maintains the BFF, the client may need to go around it if support isn't exposed for the new service in the BFF interface fast enough. So in the end, we have an added layer of abstraction to the stack that may initially alleviate some technical debt at the client level, but introduce new forms of tech debt at the BFF level. And eventually, clients may be right back to where they started anyway, when they have to implement complex data fetching logic if teams try to avoid duplication by overgeneralizing the BFF's interface, or if BFFs can't provide support for new services fast enough. So that finally brings us to GraphQL. And if you're new to GraphQL, I can provide a little bit of background. It was invented at Facebook in 2012, and it was publicly launched in 2015. Since then, it has been famously adopted by companies including the New York Times, Shopify, Airbnb, GitHub, and Netflix. It has also inspired countless open source projects related to it, including Apollo's suite of open source software libraries for working with GraphQL APIs in both client and server applications. And if you visit the graphql.org homepage, you will see GraphQL described as a query language for your API. And that's pretty high level. So from a more tactical perspective, the GraphQL specification outlines the mechanics of that query language, as well as the runtime for responding to query requests received by GraphQL API. And despite what the QL in its name might suggest, it has nothing to do with any particular database implementation. And as you begin to ramp up on GraphQL, it's easy to see what all the hype is about because it offers us the promise of a client-focused approach to developing APIs, as well as a way to evolve an API without explicit versioning. So that means a client can send a query operation like this that requests all the data that they need and in precisely the shape that they need it. And then the client will receive a response containing the data and in a shape that mirrors what they requested. And the really amazing part is that the client doesn't have to care where the data originated from on the back end, because by the time it reaches the client in the response, it has been structured in a way that reflects the relationships between the nodes in the data graph, and as though the data had all originated from a single source. But of course, we don't want clients to be able to request absolutely any data via our API. For every GraphQL API, there is a contract in place that lays out the guidelines for what's possible. And that contract is the API schema. And here we see an example of a schema written in the GraphQL Schema Definition Language, or SDL. This schema-first approach is what's used in Apollo Server, where we write type definitions in SDL and then write resolver functions to provide data for the various fields in the schema. But other GraphQL servers may take a code-first approach instead, where the full GraphQL schema is generated as an artifact of writing resolver functions for various fields that the API needs to support. And just so we're on the same page about what a resolver function is, Apollo Server needs to know how to populate data for every field in your schema so it can respond to requests for that data. To accomplish this, it uses resolvers. More to the point, a resolver is a function that's responsible for populating the data for a single field in your schema. It can populate that data in any way you define, such as by fetching data from a backend database or third-party API or an internal service. And because resolver functions can reach out to any number of data sources to provide data to the client, they are what allow us to lift data wrangling logic out of the client and onto the server side so that clients can query a single endpoint for all of the data that they need. So as GraphQL starts to gain traction in an enterprise, that adoption tends to follow a few common patterns. The first is a single monolithic GraphQL API. The second is that multiple GraphQL APIs may spring up independently with some amount of overlap between them. And the third is that GraphQL may have been used as a part of a BFF strategy. So let's explore each of these in more depth. With a monolithic GraphQL API, we end up with a diagram that's a lot easier to reason about than what we've seen so far. By placing a single GraphQL API in front of the services, the clients enjoy the benefits of having a single endpoint to query and without having to worry about what's going on behind the scenes with backend services. And a monolithic API can carry teams a long way when initially adopting GraphQL in an organization. But sooner or later, challenges may emerge around ownership of this API. In one scenario, the API may be owned by a single team, but that team may become a bottleneck in the process by which the APIs evolve to support new product requirements. This team may also be tasked with maintaining bespoke tooling to support the evolution of the schema, which can become another barrier to the speed at which the API can be evolved to support new product features. In another scenario, the GraphQL API may be jointly owned by multiple teams, or perhaps not explicitly owned by anyone at all, which can lead to governance issues such as a lack of standardization in how types are named or how fields are added to the API. Or the schema may start to evolve myopically on a client by client basis and without any kind of shared design philosophy. Alternatively, an enterprise may find itself the proud owner of multiple overlapping GraphQL APIs. This often indicates that the company was an early adopter of GraphQL, moved to production quickly, and invested more in GraphQL as time went on. As one potential outcome of this investment, an attempt to expand a monolithic GraphQL API across teams may have ultimately resulted in the API being split into multiple pieces to accommodate the conflicting needs of each team. But the trade-off then is the duplication of effort required to manage these overlapping GraphQL APIs, and also a subpar experience for client applications that no longer have a unified interface from which to request data as those graphs diverge. And related to the multiple overlapping graph situation is when GraphQL is used to implement a BFF. As we have previously discussed, BFFs have some inherent downfalls related to overgeneralization to suit multiple clients or overspecialization on a client-by-client basis that leads to tedious duplication and tech debt. And as with monoliths, when a BFF is shared, the matter of ownership can create very real challenges around schema governance and evolution. So the bottom line with BFFs is that over time, they become an expensive and unwieldy solution that often doesn't scale well, even with GraphQL in play. Now, all of the previous patterns, whether BFFs, monolithic GraphQL APIs, or multiple overlapping GraphQL APIs, also have a shared shortcoming in that their implementations result in a lack of consistency. A more productive way forward for teams searching for better efficiency and understandability from their GraphQL-based architectures will typically have two requirements. First, data graph consumers should be able to expect consistency in how they fetch data. So that means a single endpoint should be exposed to client applications, and regardless of what underlying services supply the data, clients should be able to use consistent workflows to consume the data. Second, providers should consistently represent common entities in a consumption-friendly way. And this means that teams can be empowered to use any underlying technology at the data layer, but access to this data should be consolidated through the GraphQL API and exposed in a way that complements client use cases. Additionally, teams should be able to delineate service boundaries based on separation of concern, as opposed to separation by type, and they should be able to do this without interfering with one another. So that leads us to the idea of the common data graph powered by Apollo Federation. And the common graph means that your company should have a single unified graph instead of multiple graphs that are created by various teams. But one graph doesn't mean monolithic graph in this case, because while there is only one graph, the implementation of that graph will be federated across multiple teams, where each team owns and manages some logical subsection of the overall schema, which we refer to as a subgraph. So let's explore what this looks like in practice. Federation allows teams to embrace separation of concern so that they can work on different products and features that are powered by a single data graph, and they can do this work without stepping on each other's toes. And splitting subgraphs by concern here is key because it differs from other approaches, such as schema stitching, where subgraph boundaries are often delineated explicitly by types in the schema. And on top of that, a graph router takes a declarative approach to composing subgraphs together and handles query planning for us. So we don't have to deal with the imperative pain points of other approaches to designing and consolidating distributed GraphQL architectures. So that means that backend teams can independently manage their portions of the data graph while still exposing a single GraphQL API endpoint to client developers. And in the end, we really get the best of both worlds for both front end and back end teams alike. And there are many advantages to adopting a common data graph in a company that extend beyond the obvious architectural ones. First, developers can ship code faster because you don't have to write new code to reach new data. You just extend your query and focus on the user experience. Second, products become richer because teams are encouraged rather than taxed to build data-rich experiences, and they have more time to try out new ideas. Third, decoupled teams innovate faster, so teams can work together on a shared data contract rather than on a specific endpoint, thus freeing them to re-platform independently as needed. Next, performance also improves as multiple service calls from a client become a single request with an optimized query plan generated by a graph router, and we can avoid overfetching data for the client as well. Next, observability on the graph leads to insights because graph usage metrics can reveal which clients are using which fields and for which purposes. So product managers can gain insights that help drive future product innovation. Lastly, capabilities become composable. As teams create new data and services, they are instantly available and visible to all parts of the business via the graph. And composability really is the killer feature of the common graph. On the back end, we have already seen the benefits of how cloud native enables composability at the service level. And on the front end, libraries such as React and Vue enable composability at the level of individual UI components and client applications. So we've had composability at both ends of the stack, enabled by isolated components, loose coupling, explicit connections, and a declarative approach to assembling those components. But the traditional APIs that we use to connect our composable front ends and back ends are the opposite of all of these things. And the more you layer them on top of each other, the more brittle they become. So what we really need is composability for the API layer too. And up until Apollo Federation was introduced, composability in that layer was a GraphQL pipe dream. So now that we have a better idea of what problems a common federated data graph can help solve, let's take a closer look at how all of this works with Apollo Federation. Now, the open source Apollo Federation libraries are a set of tools to compose multiple GraphQL schemas declaratively into a single data graph. First, we have Apollo Gateway, which enables you to set up an instance of Apollo Server as a gateway that serves your composed schema and routes incoming GraphQL operations across one or more subgraphs. You can think of Apollo Gateway as your graph router. And second, there's Apollo Federation itself, which provides primitives that your subgraphs use to make their individual GraphQL schemas composable. So when creating subgraphs using Apollo Server, this package will add some special Federation-specific types, scalars, and directives to the schema, as well as special fields on the root query operation type in the subgraph schemas. And everything that Apollo Federation adds to a subgraph schema is spec compliant, so there's nothing magical or vendor specific to enable this. And another really cool feature of Apollo Federation is that the spec that it's based on is also open source. So GraphQL servers written in other languages can also provide support for Federation by implementing the spec. That means you're not limited to creating your subgraphs in Node with JavaScript. You can also write them in Java, Python, Ruby, PHP, and a number of other languages too. At a tactical level, federating a schema and converting it into a subgraph with Apollo Server and Federation will look something like this. And as we can see here, all that it takes to do that with Apollo Server is to import the build federated schema function from the Apollo Federation library and use it to wrap our usual typedefs and resolvers. Doing so will add all of the previously mentioned Federation-specific decorations to our schema automatically. After that, we then pass that schema directly into an instance of Apollo server. And we can repeat this process for any number of independent subgraphs that we want to compose into the common data graph. To create a gateway, which will provide the single entry point to our common graph or clients, we then use the Apollo Gateway package. We provide the service list configuration option to the Apollo Gateway constructor, and this array specifies the name and the URL for each of our subgraphs. And for now, we just have the one product subgraph to pass in. We then set up a separate Apollo server in which to pass the gateway object, and we explicitly set the subscriptions option to false because Apollo Federation doesn't support subscriptions at this time. On startup, the Gateway Apollo server will fetch each subgraph schema from its URL and compose those schemas into a single federated data graph. The gateway then begins accepting incoming requests and creates query plants for them that execute across one or more services. So here we can see one of the superpowers of Apollo Federation. With just a handful of lines of code, we are able to declaratively compose n subgraphs into a common graph without writing any imperative spaghetti code to describe how those subgraphs should be assembled. But the gateway isn't a completely unconfigurable black box either. When needed, Apollo Gateway provides us with an interface to customize the requests going to subgraph services. Similarly, the gateway can also modify the details of its response to a client based on the results returned from each subgraph. For example, your services might all use the same authorization token to associate an incoming request with a particular user. The gateway can add that token to each operation that it sends to your services. And we can do this using the build service option in the gateway config. In this example, each incoming request to the gateway includes an authorization header. The gateway sets the shared context for an operation by pulling the value of that header and using it to set the associated user's ID in the Apollo server's context object. After adding the user ID to the context object, the gateway can then add that value to a header that it includes in its request to each subgraph service. And it's the remote GraphQL data source that allows us to modify the outgoing request with information from the Apollo server context before it's sent. And here we add the user ID header to pass an authenticated user's ID to downstream services. Now, apart from the notions of a gateway and subgraphs, one of the most important concepts in federation is that of an entity. In Apollo Federation, an entity is an object type that you define canonically in one subgraph and then reference and extend in other subgraphs. So by serving as extension points between your subgraphs, they end up acting as the building blocks of your federated data graph and are ultimately what allow you to separate subgraphs by concern instead of type. So how do we make an entity? Well, designating an object type as an entity is as easy as adding the add key directive to its definition in the subgraph schema. The add key directive defines the entity's primary key, which consists of one or more of the types fields that uniquely identify the object that it represents. And in this example, the product entity's primary key would be its UPC field. In other words, setting the UPC field as the key means that other subgraphs that want to use this entity will need to know at least that value for any product. So when used in other subgraphs, you can think of the UPC as acting like a foreign key. And the main reason for defining a key field is so that Apollo Gateway's query planner can use the entity's primary key to identify a given instance of the type. So once you define an entity in a subgraph, that's where things start to get really interesting. After you define an entity in one subgraph, other subgraphs can then reference that entity. So once the product subgraph defines the product entity, a review subgraph can then add a product field with a return type of product to its review type as we see here. Because the product entity is defined in another subgraph, the review subgraph needs to define a stub of that type to make its own schema valid. The stub includes just enough information for the service to know how to interact with the product. So that means the stub must include the UPC key field because that was the field named as the specified key in the owning subgraph. And note that the UPC field must be annotated with federation's @external directive here to indicate that the field originates in another service. And also note here that because we want to use spec compliant GraphQL, we use the extend keyword to indicate that the product type is an object type that is already defined in another subgraph. And we aren't limited to simply referencing the product entity in the reviews subgraph either. We can also extend that entity with additional fields that are defined by the reviews subgraph. When a service extends an entity, the entity's originating subgraph is not aware of the added fields. Only the extending subgraph and the gateway knows about these fields. So let's say that we want to add a reviews field to the product entity that will hold a list of reviews for that product. The product entity originates in the product service, but it makes more sense for the review service to resolve the reviews field. To handle this case, we can extend the product entity in the reviews subgraph as we see here. And for the new reviews field, note that we don't include the @external directive because this field actually does originate in the reviews subgraph in this case. So through this process of entity definition, referencing, and extension, we can see one of the other superpowers of Apollo Federation and how it enables us to split a GraphQL schema based on a more logical separation of concern and gives developers an intuitive way to interact with object types that are defined in other subgraphs. And in the end, after Apollo Gateway has composed those subgraphs together, what the client sees will mirror the original schema that we originally started with. Now, if you've worked on a GraphQL API before, you may be thinking that these type definitions all look well and good, but which service is responsible for resolving what when it comes to referencing and extending entities? The short answer to this question is that our resolvers will look much as they did before, but they will be split across relevant services and with a few federation-specific adaptations made to them. So let's take a look at how that works. In our example, the review service needs to define its own resolver for the extended product entity in its schema. The review service doesn't know much about products, but that's okay. All it needs to do is return enough information to uniquely identify a given product. So the return value of the resolver is a representation of the product entity rather than the full product object itself. A representation object only requires an explicit type name field, as well as the values for the entity's primary key fields. In this case, that's the UPC. The gateway then provides this representation to the entity's originating subgraph service to fetch the full object. For this to work, the originating subgraph, in this case products, must define a special reference resolver for the products entity. And because the review service provided the UPC in its representation that it returned from its resolver, the reference resolver for that entity in the product subgraph will have access to that value here. Lastly, we need to consider the case of extending entities with new fields. Whenever a service extends an entity with a new field, it is also responsible for resolving the field, and the gateway is automatically aware of this responsibility. Here, the generated query plan will fetch the UPC field for each product from the product service and pass those to the review service, where you can then access these fields on the object type passed into your reviews resolver. Now that we know how entity definition and resolution works, another common question about federation is whether subgraphs can share types that aren't defined as entities. For example, if you've standardized how fields are paginated across your existing GraphQL API, you may have multiple subgraphs that need to use a page info object. Alternatively, you may have a generic error object type you want to share, or a common enum, or a custom scalar type such as a datetime scalar. We could certainly namespace these types per subgraph, but a schema design best practice for GraphQL is to keep backend implementation details out of the schema. So ideally, these types would be named consistently across all subgraphs to improve the user experience for API consumers. With federation, where it doesn't make sense to expose a type as an entity, but that type needs to be used in multiple subgraph schemas, we can instead define what's known as a value type. These value types don't originate in a particular subgraph. Instead, all of the services that define a value type share ownership of it. And we have a lot of flexibility in what we define as value types because they can be scalar, object, interface, input, enum, and union types. But the most important thing to know about value types is that they must be defined identically in every service that use them. Otherwise, schema composition will fail. And for the sanity of client developers, they should also be resolved in a consistent manner across all the subgraphs where they are used. The company already has an existing GraphQL API in production. Does this mean I have to do a big bang rewrite to start reaping the benefits of federation today? And to that, I would answer absolutely not. Most of the federation projects that I see aren't a greenfield GraphQL project, but instead focus on migration from a monolithic GraphQL API or multiple overlapping GraphQL APIs or GraphQL powered BFFs. And in many ways, teams that are already running GraphQL in production in some capacity have an advantage because they can focus their energy on schema refinement and architectural considerations related to federation, rather than starting from square one with GraphQL schema modeling exercises while also having to ramp up backend and front-end developers on GraphQL. So let's quickly zero in on what a migration strategy could look like for a monolithic GraphQL API moving toward Apollo federation. So when migrating to Apollo federation from a monolithic GraphQL API, there are a few things we want to keep in mind. In general, we want to take an incremental approach. And in the spirit of GraphQL being a client-centric approach to building APIs, we want this migration to be as seamless as possible for clients. And one way we can do that is to take a strangler fig approach to breaking apart the monolithic GraphQL API into multiple subgraphs. In general architectural terms, this means that we gradually create a new system around the edges of the old. So with federation, we can begin drawing new subgraph boundaries and identifying entities one subgraph at a time. We can test and evaluate the outcome of that work and make adjustments and tune performance as needed, and then apply those learnings to the next phase of the project where we break off additional pieces of the monolithic GraphQL API. So back to our monolithic GraphQL API example, we have an API that currently uses 5 different microservices as backing data sources. And we ultimately want to migrate the management of each relevant portion of the schema closer to those microservices so that the teams that manage these services are empowered to safely evolve applicable parts of the API as needed. So the first step in this process will be to set up an Apollo gateway in front of the monolithic GraphQL API and use that API as the first subgraph behind it. So the monolithic API effectively becomes the first subgraph of the federated data graph. And from the perspective of client applications, nothing changes as long as the endpoint of the API remains the same. Next, we can migrate the type definitions that we want to belong to the user service and determine what entity extension points will need to be exposed to the monolith subgraph to ensure that the two subgraphs may be composed together. And again, from the client's perspective, it will still be business as usual, and they can continue running the same operations on the graph as they did before. Then, when we're satisfied with the results, we can do it again for the product service. And finally, for all services that need to manage some portion of the graph. And at this point, the old monolithic GraphQL API has ceased to exist, and all of the type definitions that were contained within it have now been reassigned to various subgraphs. Okay, before I wrap up, I'd like to take a moment to focus on some of the human considerations of working with a common graph and how teams can work together to evolve that graph rapidly and effectively to ship new product features. So let's start with some general best practices. First, as we have seen from the previous diagrams, federation favors decoupled and empowered teams. And we want those teams to be located as close as possible to the product or business requirements, to be empowered to design and iterate their graphs, and to be optimized for iteration speed. Next, when we design schemas for federated data graphs, we typically want to avoid exercises with the end goal of establishing idealized taxonomies. We've all heard the sirens call for an architect-led top-down ontology of an entire enterprise, but resist that urge and let your internal customers drive your schema, aiming instead for convergence toward an ideal over time. Lastly, we want to shape schemas for use cases. For example, Facebook famously and unapologetically designed GraphQL and their schemas around the needs of their apps. And similarly for most non-public GraphQL APIs, you want to design and evolve your schema in such a way that it supports product features. So these are important ideals to strive for, and when put into practice, they can have a transformative effect on the way teams work together. But if you're wondering, where are the guardrails? Or more specifically, how do decoupled teams make ongoing contributions to the common graph in a way that doesn't break down into a chaotic free-for-all? Then I have an answer for that as well. And the answer is using what's known as managed federation with a tool such as Apollo Studio. With managed federation, we use a registry as the source of truth for the schema, and each team that manages a subgraph will push their changes into this registry. And in doing so, subgraph owners can contribute changes to the schema, and the gateway can hot reload that schema as it pulls the registry, meaning you don't need to restart the gateway to incorporate schema updates. And in addition to that, managed federation also lends itself well to monitoring. So you can collect traces for operations against your graph from identified clients and ensure that an update to a subgraph won't have breaking change implications for any of those known operations over a given time period. So to get a subgraph schema into the Apollo Studio registry, we can use Apollo's Rover CLI to introspect the running subgraph and pipe the SDL output of that command into the Rover subgraph publish command. Alternatively, we can also set the schema option in the publish command to get the contents of a local GraphQL file instead of introspecting a running service. One interesting feature to note here is the Mandi-Apollo at dev option that we pass into the publish command. That string is what's known as a graph ref, and it contains the unique name of the graph before the @ symbol and the variant of the graph after. Each graph in Apollo Studio will have one or more variants, usually corresponding to the different environments where the graph runs, such as staging and production. And each variant has its own GraphQL schema, which means schemas can differ between environments. And also worth noting is that we can easily install the Rust-based Rover CLI and CI/CD environments to incorporate schema publication to Apollo Studio as a part of a relevant workflow. After doing this for all subgraphs, we can then view the overlapping composed schema in Studio. And we can also view any of the subgraph schemas individually too, and get a quick overview of what types and fields that those services own. We can also view a change log of all additions and subtractions that are made to a schema over time. And when using managed federation with the schema registry, it's worth noting that we take a slightly different approach to how the schema is composed. Instead of blindly composing it from scratch at runtime when the gateway starts up by way of introspection queries to the running subgraph services at that moment, we do it at build time when a service commit changes the schema and pushes that updated subgraph to the schema registry. By doing this, the gateway can load a schema configuration directly from the registry instead. And the use of the schema registry also gives us the opportunity to test whether a subgraph's updates can be successfully composed into the data graph before unleashing them on the gateway, which means it can proactively reject those changes if composition fails and continue serving the previous composable configuration of the graph. So to do this, once a subgraph schema has been pushed to the registry, we can now use Rover's subgraph check command to run checks against it to determine if a proposed update to the subgraph can be composed into the existing data graph without causing breaking changes. And this step is essential for teams to work effectively on distributed GraphQL architectures, because if one team references or extends an entity from another subgraph, they need some assurance that the subgraph that owns that entity won't make unannounced changes to it and in ways that would compromise the integrity of that edge in the graph. In Apollo Studio, breaking changes mean more than just composition errors too. Here we see an example of schema checks that both verify composition and test proposed changes to a schema against a known set of operations that were run against the data graph by clients over a given time period. And this is where the safety really comes in. Not only can we be certain that proposed changes to the data graph will compose, but we can also make sure that they won't cause unintended breaking changes to the clients that consume it. And if we drill down on a failed check, we can see what a particular breaking change was, what operations were affected, and either update that schema to revert the breaking change or action follow-ups with client developers as needed before this change to the schema takes effect. And finally, the way that we're able to gain these API operation insights is through federated tracing, which is another key feature of managed federation. And beyond schema checks, tracing can provide key insights into the performance of field resolution across the data graph and allow us to monitor operations for errors and help shorten mean time to recovery when something unexpected happens. So, through the safety that managed federation provides, teams can feel empowered to publish what they need to publish into the graph. Other teams can be assured that entities owned by other teams won't be changed in a way that will cause breaking changes to the references or extensions of those entities. And thus, they can feel empowered to contribute or consume a data graph where each addition to that graph amplifies its overall value. So it really creates a virtuous cycle where each team solving its own business problems creates space for other teams to leverage and build on top of those solutions. So to sum up, I hope I've helped shine a light on how a common data graph can help teams move faster, and how Apollo Federation and Gateway allow you to take a declarative approach to designing distributed GraphQL architectures. We also saw how an incremental approach can make the migration process as seamless as possible for clients actively consuming the graph. And we saw how managed federation can empower teams to make ongoing contributions to the data graph in a safe way. Now, I've only managed to scratch the surface of what's possible with Apollo Federation today. So if you'd like to learn more, I'd encourage you to check out the Apollo Federation docs at this URL. And you may also be interested in our GraphQL at Enterprise Scale ebook, which you can download for free from the Apollo website. And this guide is currently about 80 pages in length, and we're continually adding new chapters to it with content that's packed with insights that the Apollo team has gained working with our enterprise customers as they transition to federated data graphs. And lastly, if you want to take Managed Federation for a spin, you can sign up for Apollo Studio's free community tier here. And with that, I'd like to say thank you so much for checking out my talk today, and I'd be happy to take some questions.
Thank you very much, Mandi. Let's see. So questions can either come in through the chat in Zoom, and we'll be able to see those directly, or I can if they're coming through the Room C Slack channel, I can pass them on to Mandi. All right, we have one here from Slack. The question is, what is the tooling like for GraphQL, for example, viewing schemas? Or is tooling like Apollo Studio another big benefit of migrating to Federation?
So Apollo Studio can be used without federated data graphs as well. You can definitely use Apollo Studio and its related tooling, Rover CLI as well, for a monolithic data graph. Studio and Rover are very much designed with federation in mind too, though, to help make those workflows more seamless for developers. So both of those are definitely available for both kinds of data graphs.
Okay, thank you for that. Any other questions? Encourage questions. This looks like there's some typing going on, so we'll hang out for a minute or two. Well, even after the session is over, I would encourage people that come up with questions to continue to post them to the Room C Slack, and try to get those answered. I'll also take some of those links that Mandi presented at the end of the chat or at the talk, and put those in the Slack channel as well. So we have a question here. do you have a 1 to m performance issues when querying across federated graphs? Meaning accidentally having to fetch things procedurally that shouldn't be done with that much chatter.
Mm-hmm. So, I mean, ultimately, the more subgraphs you involve in a particular operation, the more network requests you're going to have to make, and there's going to be some overhead involved in that. However, there are optimizations built into the gateway and the query planner specifically to optimize how the query plan is executed across the different subgraphs that you have, executing in more of a depth first fashion than a breadth first fashion, which tends to be what typically happens with a GraphQL server. So there are optimizations that happen under the hood. And then there are other considerations you'd want to make with a federated data graph that you would want to make with any GraphQL API, such as caching or other various optimizations you can make in the web serving layer as well too.
All right, thank you. I think there might be another question coming. We're going to wait a couple more seconds since we have some time. Okay, so the question is Apollo server something that is used in the free version to get started, or for smaller teams and developers who are experimenting? And what limits does it impose in that mode?
Mm-hmm.
Oh, sorry, the question was about Studio.
Okay. Yeah, so Apollo Studio, as I mentioned, has a free community tier. You can get up and running with Managed Federation using that free tier. There are some limitations around running schema checks and also how long tracing data is kept in Apollo Studio when you're using it as your schema registry for that free tier. And then we also have additional team seat-based tier and then an enterprise tier as well for Studio. So yeah, there are some limitations on how you can use Apollo Studio if you are on the free tier. But it's certainly enough to get up and running with Managed Federation and try it out for your data graph.
Okay, great. All right, well, I think, yeah, thanks very much, Mandi. So I think we'll end the session. Like I said, I encourage any other questions to come through the Slack channel. Thank you very much again, Mandi, for presenting today at ETE, and for all the attendees. Thanks for attending, and hope everyone enjoyed it. And we'll see you at the next session. Thanks very much.
Yeah. Thanks so much, Matt.